this initial presentation provides a brief overview of fundamental concepts in energy statistics. As Nick mentioned, energy data can be used for a variety of different purposes, such as tracking and understanding energy supply and demand trends, generating energy balances and indicators, reviewing energy security, understanding energy access, informing, evaluating, assessing policy design. So the products that we use and the issues that we come across are common across countries. And to enable a common understanding, comparability of different concepts, it's important that we use common terms, definitions, methodologies in data collection and dissemination. So at IEA, our point of reference are the international recommendations for energy statistics, or IRES. And IRES is an internationally agreed set of recommendations adopted by the UN Statistical Commission in 2011, which aims to ensure cross-country data comparability. So IRES has been translated into the 6 official languages at the UN and is available for download from the UN website. And we would encourage you to download it and refer to this for your work. So we'll now look at some of the key concepts presented in IRES. And firstly, there is the scope and boundaries of energy statistics. So energy is observed all around us in the form of light, heat, chemical energy, kinetical energy, and so forth and so on. However, not all energy is included within energy statistics. Generally speaking, energy which does not have a direct impact on society, on the economy of a society, is not measured or monitored as part of energy statistics. Therefore, we need to draw a boundary around what we consider inside and outside of energy statistics, and IRES helps us to draw a boundary in this regard by providing common concepts and definitions. So these common concepts, the most important, let's say the key ones, includes energy products, which are the forms, the vector of energy suitable for direct use, such as coal, oil, gas, and electricity. Then we have the energy flows, which are the activities involving the production, trade, transformation, final use of energy across the consuming sectors. These flows are defined based on the International Standard Industrial Classification of All Economic Activities, which acronym is ISIC. Then for the production, it is an important concept which marks the starting point at which energy enters the domain of energy statistics. Here, IRES provides definition and convention, which will be touched upon in later presentation regarding the boundaries of production in the form of the energy produced, primary or secondary, and the producer type, if it's coming from a main activity producer or an auto producer, which of course have implications for where production appears in the energy balance. For example, in energy statistics, we only consider marketable production. To give you an example, coal production would not refer to the initial amount of material extracted from a mine, which might include rocks and gravel, but the marketable production made available after washing the coal to remove these impurities. Similarly, for fuel wood production, we only include the wood that is used for energy purposes, not all the wood that is also cut down to make furniture. In addition, there are conventions around how to calculate the primary production value for renewable sources such as hydropower and wind. And again, we will see them in later presentation. The energy sector, it is an economic sector whose principal activity is the production, transformation, and distribution of energy, or distribution of energy. And this sector is considered separately from other industrial sectors in energy statistics. Finally, there is the concept of reference territory. And in energy statistics, data refer to all energy activities physically taking place within the national territory of the country, regardless of the nationality or domicile of the players. This indeed differs from the residence principle, which is used in other statistical systems and which looks at the domicile of the players, not their geographical location. So let's move to what is an energy balance. Just to say that there will be a specific module on energy balances later in the course. So this will be just a preliminary introduction into this. So an energy balance is an accounting framework for compilation of data on all energy products entering, exiting, and used within the national territory of a given country during a given reference period. So at the IEA, we have 5 main annual questionnaires: coal, oil, natural gas, renewables, and electricity and heat. And recently, we have introduced also another questionnaire, the hydrogen questionnaire, that you will see later today in another presentation. And these questionnaires collect annual data on each of these main fuel groups. Although these questionnaires are interrelated, intertwined, none of them alone provides an overview of the entire energy landscape of a country. And what the energy balance does is to compile and reconcile data for all fuels and flows into a single table, providing a summary overview of the energy supply and demand in a country for a given period. So here we see an example of an IEA energy balance. And as you can see, it is a two-dimensional matrix composed of products and flows. Firstly, let's look at the columns, which show the products. So within a single column, we see the commodity balance for an individual fuel, such as crude oil, for example. And you can see all the production, trade, supply, transformation, and consumption of that specific fuel. Next, in the rows, we see each of the energy flow in the balance. For instance, all energy products exports or all fuels entering or leaving a refinery. As the name suggests, an energy balance needs to be in balance, and this means that it needs to be internally consistent so that the values in the rows and columns add up arithmetically. And horizontally in rows, the last cell, the total, is simply the sum of the values in the other cells in that row. And vertically, the logic is slightly different. There is no total row. Instead, as it will show on a later slide, there are different supply, transformation, and demand sections, which are both internally consistent and in balance with each other. So to achieve this balance, the data are presented in a single common energy unit. In this case, it's KTOE, but it could have been in terajoule, for example. And this is critical because the data need to be in a common unit to enable addition and comparison. Otherwise, the balance would be meaningless, as adding tons, barrel, and gigawatt hour would not make sense. And finally, because all data are present and shown in a common unit, we can define the total energy supply and consumption figures. These can then be used to derive some basic high-level indicators such as energy self-sufficiency, energy intensity, and so on. Please note that in this slide, in order to save space, the table shown here is just a snapshot where not all the flows are visible and many products are aggregated together. For example, here you see secondary oil products such as diesel, gasoline are aggregated together in the oil products column. The products used in our energy reporting are based on the internationally agreed definition provided in IRES, as I said, and more specifically, within IRES, there is an energy product classification system called SIEC, which stands for the Standard International Energy Classification. Here you can see a snapshot of the structure of the SIEC table in IRES. And within SIEC, products are categorized into 10 broad product families or sections. For example, coal, oil, biofuels, and these sections are then broken down into individual products or classes. For example, coal is disaggregated into anthracite, anthracites bituminous coal, lignite, and other primary or secondary coal products. SIEC also provides correspondences between each product and those shown in other classification systems, such as the Central Products Classification, the CPC, and HS, that is the Harmonized Commodity Description and Coding System. As mentioned, IRES was first adopted in 2011. Since then, the energy landscape has changed greatly, and as a result, SIEC is currently undergoing a revision, and an updated version should be released in 2026. Now let's look at the structure of the energy balance. The energy balance is broken up into two main blocks, the supply side and the demand side. And by convention, the demand side is further disaggregated into 2 or 3 other broad subsections. So firstly, we have the transformation, which presents flows of energy being transformed into another product. For example, energy entering a power plant in the form of coal and exiting in the form of electricity. Secondly, energy industry on use. It's another block which presents energy demand for non-transformation purposes within the energy sector. For example, the fuel used to provide light and heat in oil refineries. And finally, we have the final consumption, which presents the demand by the non-energy sectors and yes, the non-energy industries, such as the industry as described in the ISIC classification, residential sectors, commercial and public services, agriculture, and transport sectors, of course. So looking more closely at the supply, we see that it presents just a few high-level flows: production, trade, international bunkers, and stock changes. However, this can give us a good starting point for looking at the energy picture of a country. We can see the relative importance of the different products, the level of self-sufficiency for a given product, and whether the country is a net importer or exporter. And the sum of these flows gives us the total energy supply for a country. In the next block, below the supply, we have the transformation and the energy sector demand. So as mentioned, the transformation refers to the conversion of one form of energy to another, such as coal to electricity. And both inputs and outputs are shown on a single line in the balance. However, they are distinguished by the sign. So energy inputs to transformation are shown with a negative sign, and energy outputs with a positive sign. And the transformation is not is never 100% efficient, and there are energy losses. And these transformation losses are the difference between inputs and outputs. As a balance needs to be internally consistent, the losses are shown in the total column as a negative value. An important concept related to the second block is the distinction between transformation and energy industry on use. And for example, in an oil refinery, crude oil is transformed into secondary oil products, such as gasoline. In this case, crude oil is a transformation input, while the oil products are transformation outputs. However, the refinery also uses energy to support the operation of the refinery for lighting, heating, and motive power. And this fuel is not considered a transformation input. Instead, is categorized as energy industry on use. It is important to note the distinction as in an extended energy balance where flows have not been aggregated. It can seem like many flows are duplicated with 2 flows for refineries, 2 flows for blast furnaces, etc. But in fact, the flows are not duplicated. It's just that one refers to transformation and the other one to energy industry on use. Then we have the last block, which is the final consumption. And here we see the consumption of energy products to all final consumers outside of the energy sector, whether for energy or non-energy purposes. So, for example, industry, transport, residential, and so on. And here the data have been aggregated into the broad sector categories. However, that is just for the ease of viewing. In our extended balances, these are disaggregated into individual sectors such as iron and steel, road, rail, etc. It should be noted that under the IRS methodology, transport is a cross-cutting sector, not linked to an industry. For example, the fuel used for trucks transporting iron ore within the iron and steel industry should be reported under transport and not under iron and steel. Finally, it is important to note that the energy balance includes demand for fossil fuel-derived energy products used for non-energy purposes. For example, bitumen used for paving the roads, natural gas used for fertilizer production, or oil products used for producing petrochemicals or plastic. And it is important that non-energy use generally refers to fossil fuels only. By convention, the energy statistics does not include the production of waste or biomass, which is not used for energy purposes. So far, for example, wood destined for use in construction or furniture is not included in the production and should not also be included in non-energy demand either. So it's to be noted that in the renewables data collection, as we will see later, we have started collecting renewable fuels that replace fossil fuels used for non-energy purposes. Here we see a summary of the energy balance flows oriented from left to right rather than top to bottom. And on the left side, we see the supply, on the right hand side, the demand. And as mentioned, our starting point for supply is the marketable production after any cleaning or purification or injection has taken place. And also, as previously highlighted, an energy balance needs to be in balance, and the numbers need to add up. In an ideal world, supply and demand data would be in perfect alignment. However, in the real world, this is difficult to achieve due to issues such as data availability, measurement errors, and differences in data sources and methodologies. And as a result, supply and demand data may differ, and this difference is represented in the balance by a balancing item known as a statistical difference. And this is an important item in the balance. Ideally, statistical difference should be small, as we want supply and demand figures to be in good alignment, and a large statistical difference implies an issue with the data quality that should be investigated. So, however, care should also be taken when interpreting a zero statistical difference, because that may likely indicate data availability issues, and some values in the balance may have been estimated by setting them equal to the difference between the supply and the demand. So it would be an artificially created zero statistical difference. The sign of the statistical difference can be negative or positive. Looking at this can help understand whether data are missing or overestimated on the supply or in the demand. Similarly, the stock changes value can also be positive or negative, depending on whether a stock build or stock draw took place. And the size and the direction of stock changes can provide useful information on the market conditions. So moving to some practical reminders on conversions. There are many different units of measurement that we might encounter in energy statistics, and we can measure products in mass, volume, energy units, and in addition, depending on the country, we might use different units of measure, for instance, the imperial and metric units. So as energy statisticians, we frequently need to convert data from one unit to another, and converting within a category of units is generally easy, as the unit conversion are based on a constant. So the universal conversion, like from 1 gigawatt hour to terajoule, and from 1 metric ton to kilogram. However, to convert between categories, we need additional information. For example, we need densities to move from mass to volume, and we need calorific values to move from mass or volume to energy. Energy balances are based on energy unit. However, some data are more commonly collected in physical units, for example, tons of coal, and therefore both accuracy of both the calorific value and the underlying physical energy data are important in ensuring accurate energy balances. So to expand a little further on calorific values, as said, the energy balances express information in energy units, and in order to convert from physical unit to energy units, we need to use a conversion factor, the value of which will vary depending on the type of products and its quality. We call this conversion factor a calorific value. So calorific values represent the heat energy released when the fuel is combusted, and different fuels have different calorific value. For example, jet kerosene contains far more energy per unit of mass than lignite. However, the calorific values can also differ within the same product. For example, bituminous coal in New Zealand has about 50% more energy content per unit of mass than an equivalent amount in Kazakhstan, and therefore using the Kazakh NCV in place of the New Zealand NCV or vice versa would affect dramatically and distort the efficiencies and energy flows observed in the energy balance. Therefore, it is important to collect information on NCVs from industry at the time of collecting the information on the physical quantities. Calorific values can also differ by flow. For instance, a country may produce and export coal with a low NCV, net calorific value, while at the same time importing coal with a high NCV for use domestically in iron and steel or power plants. So the NCVs can provide an important tool for validation, as knowledge of historic or expected ranges can be used to validate the data. So to conclude, just a few final comments on the benefits of collecting energy statistics. First of all, reliable, accurate, and timely energy data are indispensable for policymakers to enable sound, evidence-based decision-making, as we have said since the beginning of this training. So these can include the development, formulation, and monitoring of energy policies, such the ones related to energy transition, but also enabling the monitoring and reaction to energy security developments, such as for supply shocks, for example. And in addition, it can also feed into other areas such as development, energy access, health, environment, etc. Reliable data are also useful for the business community in terms of analysis, planning, and for providing market signals. In addition, they can also be used for international collaboration and benchmarking. And they can also be used for and by the general public in terms of raising awareness, promote understanding of energy usage, and by researchers and students in academia. So we can also combine basic energy data with various other data sets, some as socioeconomic data like population and GDP to generate a variety of useful indicators. For example, here there are some examples of energy indicators related to the economy of a country that are shown in IRIS. And for example, energy intensity indicators such as the amount of energy used in a given sector compared with the economy output in that sector. And energy data can also be used to generate a variety of interesting and different indicators depending on user needs, demand, and priorities. And of course, that is subject to data availability. Here we can see an example where we see the change in total energy supply per capita and per unit of GDP in the world over time. And similarly, using energy data, we can apply the greenhouse emissions factors and methodologies provided by the IPCC to generate estimates of CO2 emissions from fuel combustion. And of course, we can move beyond the high-level data that are shown in the energy balance and zoom in to look at more disaggregated end users consumption. For example, breaking the residential energy consumption down into energy used for lighting, space heating, or space cooling, and using this information to create more advanced energy efficiency indicators, which can be effective for tracking the success of more specific energy policies. However, of course, this requires more detailed data, which may require changes to data collection templates or running specific surveys, and therefore it is important as energy statisticians that we periodically review our data requirements to ensure the continuing relevance of our energy statistics.